Everyone kind of has their own definition. But generally it involves some combination of the following things. Using functions, obviously that's kind of in the name for functional programming. Avoiding side effects, so we try and write pure functions that don't have any kind of side effects. First class functions, so we treat functions just like any other objects, we assign them to variables, we pass them into other functions. Laziness, we don't compute things when we don't have to, we do work kind of on demand. And immutability, we don't mutate our variables. Once we try and assign to something, we don't assign to it again. And so these are kind of themes that you'll see throughout this talk. And so in particular, we're going to talk about functional programming in Python. And in Python 3, a lot of what I'm doing here is really Python 3 specific and won't work in Python 2. So I'm kind of a recent convert to the Python 3 bandwagon. So that's my other thing I can pitch to you about. To start with, there's this operator module, which has functional versions of all of the operators like add, subtract, less than, greater than. So if you want to use add as a function, you can import it from operator and use it as a function. There's also a module called functools. And the most important thing to us from functools is going to be partial, which does partial function application or currying. So for instance, if I want a function that adds 1 to a number, one way to do it is just to define it as I defined it up here. Add 1x is return add called on 1 and x. But using partial, I can just say add 1 is the partial function with add where I curry the first argument 1. And so if you want to pass add 1 into another function, for instance, this can be a really handy way to do it without having to define another function. And we'll be doing that a little bit. There's also reduce, which is basically a way of folding a list of numbers into a single number. It got stuck in functools because Guido does not like it, because every time he sees it, he has to grab pen and paper to diagram what's happening and figure out what it's supposed to do. This criticism is also going to apply to almost everything we're going to do today, so don't tell him about this either. Within Python, if we want to get functional, we end up talking about iterators. What is an iterator? It's something you can call next on and get values one at a time. So in Python 3, if I have a list, I can call iter on it and get this iterator. And then I call next, I get the first value 1. I call next, I get the next value 2. I get next, I get the next value 3. And I call next when there's no more values, and I get this stop iteration exception. And it's Python, so exceptions are fine. We don't sweat them. That's what we expect to see when an iterator is done. You get stop iteration. So typically we don't call iter itself. Instead what we do, let's take a step back. The nice thing about using next is that we can generate these values on demand. And so when we talk about doing things in a lazy manner and not doing computations until we actually need them, this is what allows us to do that, and we'll be able to create lazy infinite sequences, which we'll be using a lot of in kind of crazy ways. So usually what you do to get iterators is you can use these generators, which are functions that have this yield statement in them. So what does this do? If you call lazy integers, and then you call next on it, it will go until it sees the yield, it'll return that value, and then it'll pause and remember where it is. Then when you call next again, it'll go back to where you left off and keep going until it sees another yield, and so on. So for instance, if I call next on this lazy integers, it sees while true, goes into an infinite loop, yield 0, stops. Then I call next again, it goes back, adds 1 to n, and repeats the while loop, yields 1, and so on. So that this function, lazy integers, really returns every integer from 1 up to, there is no up to because there's no biggest integer. So you can take the first 10, you can take the next 10, and you can just keep on taking it forever and ever. You can also do generators by doing what look like list comprehensions, but with parentheses. So you can define the squares by saying x squared for x in lazy integers, or doubles 2 times x for x in lazy integers. When you define that, it's not computing anything. It's just defining this generator object, but until you either call next on it or pass it into a for statement, it's not doing any computations. Then when you call next, it'll do the first one, next it'll do the second one. And in particular, if you use square brackets, it will try and compute all the lazy integers, and you'll be in a bad spot. So you don't want to do that. One way to think about these is in terms of pipelines. So if you're using Unix and you want to see how many times in my project Euler Haskell file I've used the word prime, you can cat it and then pipe it into a grep and then pipe it into a word count. You could do something similar in Python, open the file, lazily get all the lines, lazily filter all the lines that have prime in them, and then not lazily count them. And in this particular sort of situation, you have to be careful. If you let that f go out of scope before you actually force the evaluation, then you'll get an error. And we won't do any more of this. Instead, we're going to talk about my new best friend, which is itertools. Itertools is a module in Python that has all sorts of functions that are useful for dealing with iterables. And until you use it, you'll look at them and say, I don't know why I would ever want to use that. And then after this talk, you'll say, I don't know why I would ever want to use anything else. The simplest one is probably count. Count takes a start and a step, and it just generates all the numbers. So if you just do count with no arguments, that's basically our lazy integers. It generates 0, 1, 2, 3, so on. There's also this islice, which will take a slice out of a sequence. So you could say, I want all the elements from 3 until the end. I want all the elements from 7 to 9. I want the first 8 elements. And so islice will lazily do this. You say, I want the first 20 elements, but it won't evaluate those elements until you force it to evaluate them. There's also this function called t, which is not usually useful, but when it is, it's very useful. It takes one of these iterators and it splits it into multiple copies that remember their values, so that if you want to iterate over them multiple times, you don't have to do the computation every time. It remembers the computations for you. And so that can be more efficient. There's also repeat. Repeat is really simple. It repeats a fixed element a certain number of times or forever. So if you call repeat 0, that's just 0, 0, 0, 0, 0 forever. There's cycle. Cycle takes something that looks like a list, and it just cycles over the elements. So if you pass in 1, 2, 3, it'll give you 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And that can be useful in a few situations. There's chain, which if you have multiple iterables and you want to run through one, and then another, and then another, it will just go through the first elements one at a time, then the elements of the second one at a time. And then probably the most difficult one that we'll be using is accumulate. Accumulate takes a sequence and it generates all the running totals. So the first element, if you pass in add as the function, the first element of the accumulated sequence will be the first element of the original sequence. The next element will be the first element plus the second element, and the first element plus the second element plus the third element. But you can also pass in other functions. And in general, you'll be doing the sequence where every element is the function applied to the previous accumulated element plus the next element of the original list. And so we'll be doing that to do various forms of magic. And so here's where we start going down the rabbit hole. So to start with, itertools does not have all the itertools that we need. So we need a few of our own. For instance, we will want to realize the first several values of a sequence. So there we can use islice to get a new sequence that only has that most first n elements, and then we use a list comprehension to actually force their evaluation to get them back in the list. So if you call take 10 for some iterable, it will give you the first 10 elements and compute them. Similarly, we want a drop function, which will say, I don't want the first n elements, I want all the rest. Again, we just use islice and say, give me the elements starting from n and ending at none. We'll want to be able to look at the first value of a sequence. In Haskell, that's called head. Here, it's just the same thing as our next function, so we can just do it that way. And tail, we'll just want to drop off the first element and return the rest of the sequence. Here, we can do partial function application. That's just I want to drop the first element. So here's an example of using partial. We're also missing a function that's called iterate. Iterate, given a function f and a starting point x, should give us the infinite sequence x, f of x, f of f of x. So every element is just f applied to the previous element. So one way to do this is with a generator. We say to iterate f on x, first yield x. So the first time you call next, you'll get x. Then yield from, and yield from is this amazing addition in Python 3, which is basically the same as doing for x in whatever yield x. So yield from, and then we iterate f over f of x. So this works, but Python is not clever about optimizing away recursion. And so eventually you'll get too many recursive calls, and this will blow your stack. Here's a different version. While true, yield x, and then replace x with f of x. So this one won't blow the stack. It has no recursive calls. It's just a while loop. But we're continually reassigning the value of x. And that's the mutation that we're trying to avoid when we're being like purist dogmatic functional programmers. So how can we avoid that? Well, we can avoid that using accumulate. And so this is my crazy functional version. We accumulate on the series repeat x, this function that I've defined here. So what is repeat x? Repeat x is just the sequence where every element is x. And if you remember accumulate, that was the partial sums running total function, where it takes the previous accumulated element, the next element in the original sequence, and does some function of them. Here we're saying take the previous accumulated element, ignore the next element in the sequence, and just call f on the previous accumulated element. And so this is going to give you x, which is the first element. Then it'll call f of x, f of f of x. So this is a really pure functional version, and it doesn't have recursion problems, and it's awesome. So we're good with it. So how would we use this iterate? Well, if you remember how we did lazy integers before with a loop and a yield statement, here to do lazy integers, start with 0 and call add 1, and then call add 1 and call add 1. So here's a version of lazy integers. It's very simple. Iterate add 1 starting at 0. So one of the fun examples when doing functional programming is Fibonacci numbers. So 1, 1, 2, 3, 5, 8. And every element is the sum of the previous two elements. So here's kind of a naive way you might write it if you had to do a coding interview. You'd say, OK, if n is 0, return 1. If n is 1, return 1. Otherwise, call fib on n minus 1, call it n minus 2, return the sum. As you know, this version is really inefficient because when I want to do fib 10, OK, well, that's fib 9 plus fib 8. Fib 9 is fib 8 plus fib 7, so I'm computing fib 8 twice, and you just get this explosion in how many times I'm computing this. And so you really would never want to compute them this way. So here's another way. Let's just compute the infinite sequence of Fibonacci numbers. Start with a and b, 0 and 1, and then go into an infinite loop. Yield b, replace a with b, replace b with a plus b. This is efficient. It runs fast. It gives the right results. And again, it has all this like awful mutation that as dogmatic functional programmers, we want nothing to do with. So this is my Haskell version. And it's very cute, and it's also pretty terrible. So we say this sequence is given by yield 1, yield 1 again, and then yield all the elements from, I'm going to map the add function across the sequence of Fibonacci numbers and the tail of the sequence of Fibonacci numbers. So the first element, I'm adding the first element of fibs, second element of fibs, then the second and the third. So this does the right thing, but because of the way it's constructed, every time we get to that map statement, we're recomputing the fibs again from scratch. And so if you try and take the first 30 Fibonacci numbers using this method, it will take, on my computer, 8 seconds, which is too long. So if you remember itertools T, that's for creating multiple memoized copies of an iterable that will make it so you don't have to repeat computation. So I'm grateful to some commenters on my blog who pointed this out to me. So if you do this version, yield 1, and now instead of making 2 recursive calls to fibs, I use T and assign them to variables. This version is actually very fast. It takes 0.2 seconds. Oh no, that's actually much less than that. Those are microseconds. But it feels kind of clunky. So here's another approach. Given a pair of numbers, x and y, or a and b as we called them before, the next Fibonacci after them, we can represent it as the pair y and x plus y. So this is kind of what we were doing before with the while loop, but with no mutation. This is like a pure function that takes an input and spits out an output. And now we can define our Fibonacci sequence as a generator comprehension. I want the second element of every pair for the pairs in calling iterate next fib, starting with the pair 0, 1. So this is like a really nice functional feeling way of doing this. And as a side benefit, it's really fast. Just for fun, this is the Haskell way of doing prime numbers, which has kind of the same flavor. If I want to filter the primes out of some iterable, I pull off the first element p, I return it and say that's a prime, and then I take the rest of that iterable and get rid of everything that's divisible by p. So it's your standard prime number sieve. And so to find all primes, you just start that with count 2, which if you remember is a sequence 2, 3, 4, 5 going on forever. So when I call filter primes on that, it pulls off the first element 2, says 2 is the first element. Now take what's left, which will be the numbers from 3 on, get rid of everything that's divisible by 2, and then do it again. You pull off 3, get rid of everything that's divisible by 3, 5. And so this is how you might do primes. Okay, so I'm sure you're wondering, especially the people who are leaving, what does any of this have to do with data science? And so I fall back on, this is kind of my standard example, k-means clustering. We have some points, we'd like to group them into k clusters, and we want the clusters to be small in some sense. So here's an example, I picked some points, and I said I want 5 clusters, and they're colored according to their cluster. The star is the middle of each cluster. So the way we typically solve this problem is with an iterative approach. We choose some k-means to start with. Each point we assign it to the cluster corresponding to the closest mean. Then based on those clusters, we compute a new set of means. And we just repeat this until we get to some stopping point. And just as one caveat, this implementation is supposed to be expository, not efficient. Once I talked about this and people were kind of murmuring in the audience that what an inefficient way to solve this problem, that code would run forever, like how dare you. So that's how I dare. So you might try this with a not functional approach. So here's a class, k-means. It has a constructor, and in the constructor you say, here's how many means I want. I want 5 means. Okay, I'll remember that in a variable, and I'll set up these means as just a list of none to start with. And let's say that I have the means, then how do I predict the cluster for a given point? Well, this is sort of elaborate, but all I'm really doing is saying, find the index of the mean that's closest to this point. So I start off with an infinite distance. For each of the means, I check its distance. If it's smaller than the best one I've seen so far, that's the new prediction, and then I return it. So nothing fancy here. How do I find the means? Well, I start by just picking k of the points at random. And then I've chosen a number of iterations. Let's say I'll run this 10 times, and that'll be good enough. So 10 times, I will do the following. Assign each point to its closest mean. So just assign point I to whatever the prediction is based on those means. And then compute new means. So figure out what the clusters are based on those assignments, and compute the mean of each of those clusters. And I repeat that, the means will go somewhere. So if I do this, I start with 100 points in the unit square. K means 5. I fit the model on those points, and I do the predictions. I can plot those and get the same graph I showed you before. So what would it look like to do this in a more functional way? Well, to start with, we'd use a function instead of a class. So we have a function k-means, which takes the points and the k and the number of iterations. And we want this function to return us what are the means of the clusters that we get for these points. So we start by picking k the points at random, same as before. And now for each iteration, we say the means equal the result of some function we haven't written yet called new means. New means takes the points and the means and returns the next set of means. So this is a functional feeling way of doing it. But again, we have this variable means that we keep reassigning to and keep reassigning to and keep reassigning to. As dogmatic functional programming zealots, we don't want to mutate like that. So instead of thinking about k-means, we can instead think about k-meanses. which was the best name I could think of. But basically, as we go through this process, we generate a set of means, and then each iteration we generate another set of means, and then the next iteration we generate another set of means. And so I think of all these sets of means as meanses. And so instead of writing a function to generate means, we can write a function to generate meanses. Okay? So this is kind of a more crazy functional approach. Given a set of points and given k, we're going to return an infinite sequence of meanses. Okay, so the initial means, again, we just start with pick k of the points at random. And now we're just going to iterate partial new means points on initial means. What the heck does that mean? Okay, so partial new means points, remember partial is partial function application. Our points are never changing, like we pass them into this function. So it's fine to curry them to make a new function. And once you curry those points in, partial new means points is a function that maps a previous set of means to a next set of means. And if you remember, iterate takes a starting point x, calls f of x, calls f of x. So if you call iterate on that function that maps old means to new means, and you give it the initial means as a starting point, you're generating the lazy infinite sequence that's the initial means you gave it, the next set of means, 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 and next set of means, and so on forever. So if you want to run it for 10 iterations, you say the meanses are take 10 from the k-meanses function. If you want to run it till it converges, well, then you just say the meanses are until convergence of that infinite sequence. And so why is this interesting? Well, one reason it's interesting is that once we generate these meanses, we can look at them and see how is this convergence happening and what's going on at every step of the process. Not just what are the 5 means that got spit out at the end, but how did those 5 means happen? So how would you run an iterable until convergence? One way to do it is just to remember the previous value. So previous is none, go into an infinite loop, pull the next value off the iterable, and if it equals the previous value, we want to stop, so you raise that stop iteration exception. Otherwise, you yield the value, and then you set previous back to the value. But again, as dogmatic functional programming zealots, we don't want to be reassigning value and reassigning previous all the time. So another way to do this is to use accumulates. We'll say to do an iterable until convergence, we accumulate iterable with no repeat as the sum function, where no repeat is simply given the previous value and the current value. If they're equal, you raise the stop iteration exception, and if they're not, you return the value. So start with the first value, take the second value with the first accumulated value, which was the first value. If they're the same, you stop. If they're different, you make the second value your next accumulated value, and then you keep going. You could also do something similar if you had floating point numbers and you want to run this until they get really close. Okay, well then we can do an until nearly convergence. Just give it a tolerance and accumulate by doing, instead of a until they're the same function, you do a within tolerance function. Meanwhile, we sort of punted. We still need a new means function, but that's not hard. We do our assignments by just saying for each point, find the closest index of the old means. We do the clusters by saying for each index, find the points that are closest to that index, and then we just compute the mean of each of those. To find the closest index, we did this before. Minimum distance is infinity. Iterate over the means, and for each one, check the distance. If it's smaller, make that our assignment, and then return our assignment. But again, we're mutating. So how can we do this in a more functional way? Okay, so here we find the closest index by just saying, let's create the list of distances using list comprehension and return min of enumerate distances. Enumerate adds the index. So enumerate distances turns them into a pair, 0 first distance, 1 second distance, 2 third distance. And passing it this key function that says we want to find the minimum based on the second value. But it will still return the pair. And then we want the first value of that pair, which will be the index. So that's a more functional way of writing closest index. Square distance is very simple. It's just summing up the squared differences of the elements. And cluster mean is also pretty simple. We basically do the index-wise sums and divide by the number of points. So as an aside, I just learned this trick a few days ago, but Matplotlib will make animations for you. All you need to do is import animation and define a function animation frame, which takes a frame number and does something Matplotlib that corresponds to that frame. So get the data based on the frame number, plot the data, and if you have ImageMagick installed, you can write them out as animated GIFs. So for instance here, I pick 500 random points in the unit square. I compute the list of meanses that runs until convergence, and I pick 5 colors. And K here is 5. And so what does my animation frame look like? Well, for frame 1, I want the first or the 1th element of the meanses series. Compute the assignments in the clusters, plot the clusters, plot the points, and color the points. So if I do this, you can actually see here is the sequence of means as it goes and converges. And the points get recolored. So you can kind of see what's happening. That it starts off somewhere random, but eventually it gets to a point where 1 cluster is right in the middle and 4 clusters are right in the corners, which is probably what you'd expect. So here's a different random data set where the x coordinates are 0, 1, 2, 4, 5, and the y coordinates are a normal variable. I couldn't really tell you why I chose this, but I did. And again, you can see that the means kind of move around kind of as you'd expect, but it's kind of neat and fun to watch. All right, so how else can we apply this to data science? Well, another place where this turns out to be pretty interesting is gradient descent. A lot of models that we use involve taking minimums of things, taking maximums of things, solving optimization problems. So gradient descent is where we minimize a function by computing the gradient, the vector partial derivatives, and taking small steps in the opposite direction. For example, let's say you want to find the minimum of some function where it's just the sum of the squares of all the elements. So you pass in a list of numbers, and it's the sum of the squares. Now, being data scientists, we know that that minimum is going to be when all the numbers are zeros, but let's pretend that we don't know that and kind of proceed. So if you remember your calculus, the gradient of this function is just 2 times each coordinate. So now we need to say, well, how do we take a gradient step? Well, to take a gradient step, we need to know a few things. One is the gradient function. The second is a parameter alpha, which says how big do we want the step to be. And the third is the point x, which you say, which is the point we're starting from. So starting at the point 1, 1, and given that gradient function I defined on the previous page, and given a step size of, say, 0.01, where do I end up after taking that gradient step? So I just say, I'll zip together the point and the gradient, because I want to move each coordinate corresponding to that point. And to each point xij, I add that factor alpha times the jth component of the gradient. Gradient step is a nice pure function. And suggestively, if you take it, for a given problem, you might want to keep df, the gradient function, fixed and alpha fixed. And if you curry those, then you have a function that maps from a point to a next point, which should seem kind of familiar. Because you can just use iterate. And there you've written gradient descent. So what is this gradient descent doing? It's saying, let's iterate that function, which takes a point and maps it to the next point on the starting point. So you get the starting point, you get the next gradient step, the next gradient step, the next gradient step, the next gradient step. So this is 6 lines of code, and it would probably be 4 lines of code if I use a smaller font, which I did not do because I care about your people's eyesight. But this is basically a working implementation of gradient descent right here. So if I give it that function, which is the sum of the squares, start at a random point and say, run it for 100 steps and show me every 20th value. Well, The first value is just somewhere random, 0.35, 0.89. But you can see that it very quickly moves to points that are very close to 0. So I can use the same animation trick and say, you know what, I want to run gradient descent on just 2 variables, x squared plus y squared, starting at 50 random points. So I function to define a random point. I grab this giant matplotlib list of colors, and I say I'm going to get a length 25 path for each of 50 different points. So for each of 50 different points, I run gradient descent 25 steps, and I store that as a path. And then I just say I want to animate this. So in the nth frame, I'll draw the nth step for every one of these points. And so you can see that no matter where they start, they always go right towards 0, as you would hope. So nothing too exciting. We could have solved that ourselves. So here's a slightly more complex function. It's exponential negative x cubed over 3 plus x minus y squared. Has a minimum at x equals 1, y equals 0, and a saddle point at x equals negative 1, y equals 0. And so if I do the same to this one, you get a little more interesting picture. You can see all the points running off along the gradient lines. But I'm not really here to talk about calculus. I'm here to talk about data. So before I do that, let's take one side step, which is a stochastic gradient descent. So in that previous example, we were just trying to minimize a function of a single point. But when we're working with data, a lot of times we're saying, let's find the parameters that minimize some error function across our data. And a lot of times those error functions are additive, so that the error is the error on the first point plus the error on the second point, the error on the third point. And so one approach is to use gradient descent on the sum of the error functions to find the optimal parameters. But a lot of times that's slow. And so what you do is you just take a gradient step on one point at a time, and you do that for each point. And so here, our data is fixed. And so if we curry them, we're trying to find an optimal value of some parameter beta. So this is a function for taking a stochastic gradient descent step. It's not that different from the previous function. The only real difference is that instead of just having an x, it has a previous beta and then also the point that we want to take a step from. So we take the point, which is an x and y pair that we want to take the step from. We get an x and a y out of it. And we take the same gradient step based on the gradient. And then to implement stochastic gradient descent, it's just these 2 simple lines of code, which are not that simple. So what is this code doing? So if you remember chain takes one iterable, returns all the values from it, and then takes a second iterable and returns all the values from it afterwards. So this chain I have right here starts with a list containing just beta 0. So its first element will be beta 0. And then after that, it calls cycle on zip xy. Zip pairs together corresponding elements. So the first element of zip xy is the first x paired with the first y. The second element is the second element of x paired with the second element of y. And cycle will just repeat those over and over and over again. So that xy is a sequence starting with beta 0, then x0, y0, x1, y1, x2, y2, until you run out of points, and then starts over again, x0, y0, x1, y1, x2, y2. Okay, so why would you want to do that? Well, if you curry the stochastic gradient descent step function that way, it becomes a function of previous beta and xyi. So that's basically our partial sum again, where we say the previous value is a beta, the next value we're picking off is an x and y pair. I take those and combine them to find a new vector of parameters. And so this will give us an infinite sequence of betas that get better and better for minimizing our error. So in particular, we're going to apply this to linear regression. I'm sure you're familiar with the linear regression model. Y equals x beta plus some error term. So here, x is just a constant value and then also a random number, 100 points. Y, we're going to set it up so that It really is a linear relationship. So fixed constant of -5 plus 10 times the second coordinate, and then plus some random noise. And so to predict with this model, you just say that's the first coordinate of x, which is 1, times the first coordinate of beta, plus the second coordinate of x times the second coordinate of beta. So very straightforward, what they teach you in Stats 101. And so we typically do this using a least squares estimate. So trying to minimize the squared errors. So the error is just the difference between the prediction and the actual value. The squared error is the square of that. And the squared error gradient is just a tiny bit of calculus, which I'm not going to go through, but you can do for fun. Just calculus is fun. So how would I apply the stochastic gradient descent to linear regression? Well, here's my data set. I start with a totally random beta 0. So just random value of the first coordinate, random value for the second coordinate. And then for the results, I just pick a number of steps and generate the infinite sequence of betas generated by running stochastic gradient descent using that squared error gradient function on x, y, beta 0, and a small step size. Take the results and animate them just by plotting the regression line. So the regression line goes through those 2 points. And so you can watch, here are the regression lines that get generated by the stochastic gradient descent process, which is kind of hypnotizing and fun to watch, although not more fun than Netflix. And so what is the moral of this story? IterTools is awesome, laziness is awesome, infinite sequences are awesome, and Matplotlib animation is awesome. So that's it. Thanks for coming. Check out my Twitter. Check out my book. Here's a code if you want to buy it from O'Reilly and get 50% off. The code for all this is up on my GitHub right here. And if you do anything cool with it, I would love to hear about it. And if you have any questions, I think I have a couple minutes. Yeah.
So for those of us that functional programming is not intuitive, is there any way to make that easier other than just banging your head against it?
Tell me more about which part of it is not intuitive. It's not intuitive that it's good to compute values lazily. It's not intuitive that you don't want to mutate variables. It's not intuitive that you...
Well, it's not like I look at the code and I start building a chain in my mind of what goes into what, and then I'm like 9 levels deep in session and I got shot and died.
That was a very popular movie, right? That's a good question. So I'll tell you what I tell everyone, learn Haskell. Learning Haskell has totally warped the way that I write Python, as you can very clearly see. Haskell is like the gateway drug to functional programming. I think that coming at this from like a purely kind of Python or Python, C++, Java background, it's harder to appreciate a lot of these things, where if you sit down and do Haskell, or to a lesser degree like Camel or Clojure or some of these other more functional languages, Scala, F#, you can appreciate it more.
Thank you for the talk. I think a lot of overhead of writing functional programming in Python is because it's dynamically typed. Usually when you work with functional languages, they're statically typed. Once the program compiles, you know it's probably going to work 90% of the time. But with Python, like, you define these arguments which can be arbitrary typed. So when you train them together, you have to manage this entire type system about what goes into what is the type, what is the value type of iterator when you evaluate. And then often you don't know whether it works until you run it. Right?
So I sort of agree with you in the sense that probably my biggest gripe against Python is it's not typed. I sort of disagree with you because Clojure is not typed, and it's a very popular functional language, right?
So can one just use Cython to type everything from the beginning and apply your
To use what?
Something like Cython where one is declaring types and
It's a good question. I've never worked much with Cython.
so Cython does away with dynamic typing.
But it's C types, not Python types, right?
That's right.
Yeah. And it's not going to get you the power of like a real, type system with union types and things like that. Yeah.
So we've seen that this works really well with infinite laser sequences, Fibonacci numbers, stochastic gradient descent, et cetera. Have you, and k-means are another great example, how does this approach fare with other similar algorithms? I don't know, other things like doing classification problems, et cetera?
So one, I wouldn't say that it necessarily fares well with any of these algorithms I showed you. I think it's interesting to apply to these algorithms I showed to you, and that it makes cute animations. And so I haven't tried it with any others. Those are the ones that I came up with for the talk. My suspicion would be the same, that pretty much anything where you're doing an iterative process like that, treating it as this lazy infinite approach is an interesting way to approach it, and will give you interesting visualizations and more understanding into the process than something that just spits out the final values. But would you actually want to build your production Python code this way? Probably not. Yeah, in the back.
I do a lot of functional programming, but I haven't really made the leap to building my own classes. At what point do you feel it's necessary to really do that, and what do you think is a really good resource to make that jump?
What do you mean by building your own classes?
I'm not constructing my own objects, including various attributes that I need to, carrying it all around. I just don't do a lot of that. Like, small functions and how those function.
I would say that I don't think of constructing classes and like carrying attributes around with them as something that's really core to functional programming. I think of the small functions aspect as being more core to it. So.
Follow up to that first question. I'm not a functional programmer, and I've heard a lot of people rave about functional programming, but I've never understood just exactly why it's awesome. I mean, we talked about, why immutability is awesome, why laziness is awesome, but or that they're awesome, but I haven't seen why they're awesome. So could you go into a little more detail?
Sure. So laziness is really nice because one, you get kind of efficiency gains because you don't compute things you don't need to, and two, it enables some really interesting things for free. For instance, in Haskell, if you ever do dynamic programming, you don't have to do any work for it. You basically say, here's an array with my values, and because of laziness, the first time I need a value from this value from the array, if I define it as dependent on these other values, the dynamic programming happens for free. In terms of the immutability, a couple things. One, immutable code is generally considered to be easier to reason about. Once a variable is assigned, you know it's going to have the exact same value. You don't end up with things like race conditions because no one's modifying the variables. It makes things like concurrency and distribution a lot easier because think about all the complexity you get when you're trying to like synchronize things, right? When you have immutable variables, you don't have to synchronize anything because you're never modifying anything. So I think people would say that's one of the huge gains you get.